Hello YouTube! Let's have a look at acceleration. And acceleration is really a wonderful thing because it's very much similar to velocity. Let's look at it. What's the definition of acceleration? Well, acceleration is velocity over time. So velocity is space over time and acceleration is velocity over time. That's very similar. And you're going to see it's very similar to velocity, just that instead of space you have velocity right here. And you can, of course, get the velocity from having acceleration and time, and of course you can get the time from having velocity and acceleration. We all know that because we have learned it in the last video about velocities. Now let's get a step further and talk about what happens if the acceleration isn't constant and we don't have initial conditions of 0 meters per second and 0 seconds. So let's look at that, and we're going to get this formula. A is delta V over delta T. That's exactly what we had for velocity. Velocity is delta X over delta T. So again, we have a very similar formula here. And if we want to get the velocity, we take acceleration times T minus T0 plus V0. We know we can get that from forming this here to V. Of course, by assuming that we have the end V minus the initial V and the end T minus the initial T. And of course we can also get the T. That's nothing new. We already knew that by the video of velocities, just that we had there, instead of an V, we had an X, and instead of the A, we had an V. That's very similar elsewise. So let's look at the last definition. That is, A is the derivative in respect to time of V, and V is the integral of A with respect to time from T0 to T plus the V0 again. And if we want to once again have the time, we can take the function A of T is equal to something with a T, and take the T out of it and get everything to say T is equal to some function of A. Of course we could do the same with V, and of course we could do the same with X of T. And of course this also applies once again for our vectors. So if we want to have the vector acceleration is nothing else than the derivative with respect to time of the velocity vector. So once again we can do that. But we have talked about that already, about all of that in the video about velocities. Just instead of an A we had an V, instead of the V we had an X. So there's nothing new here, or is there? Well, we're going to talk about something new, and that's, for example, how the acceleration does with the space. So we have an X coordinate and we have an acceleration, which means that we can get the time, and I'm going to show you exactly how that is done. If we assume that our acceleration is constant, of course, we get this nice formula right here. X is 1/2 AT squared plus V0 times T plus X0. And that's very important. That's a formula you should remember. This formula has another form, which is this down here, in which we took a T0. And the T0 is not really important if we talk about measuring the time from 0 seconds. Sometimes we want to have an initial condition of T, so sometimes we use this formula right here for constant accelerations. Of course, if our acceleration was not to be constant, we would have this nice formula right over here, and we would have this nice integral. Now, if we assume once again that the acceleration is constant, we are going to see that this formula, this unspecific formula, leads to this specific formula for the specification of A is constant. And let's look at that. How does it work? Well, we assume A is constant, so that's our first if, and then we take this integral, and if A is constant we can do this integral. Because A is a constant, that's just A times T, or A times T minus A times T0, because we have the from T0 right here. Of course, if you want it from for this formula, you can just leave t0 as 0. That's no problem then. So what you also have is, of course, the v0. You also have to take that. So in the end, you have a times t minus a times t0 plus v0. That's your velocity. Now we can get the x coordinate by integrating over the velocity and adding x0. So let's do that. Let's just integrate over the velocity and add x0. So we do that and we get this strange 1/2 right in front of here, because if we integrate over x, it's 1/2 x squared, because if we derive 1/2 x squared, it's x again, because the 2 comes from the exponent x squared, and we derive that, the exponent pops in front. And if we want to integrate over x, we get 1/2 x squared, because the exponent is going to jump in front, and we're going to get 1 times x. So that's wonderful. So this is why there's 1/2 in that strange formula, just because it's integration. Now, if we do it like integrating, we get this formula. And I'm not showing you the step that comes in between these two steps, because it's quite difficult. If you just integrate it with respect to t and then add the x0, it's okay. This comes out. If you want to do it step by step, then follow me, because I have written you down how it looks step by step. So this is the first step. We just integrate in with respect to t, and we get this is the antiderivative of this right over here, and we subtract from that the antiderivative evaluated at t0, because we start from t0 in our integral. Now we add x0 at the end, because it says so that we should add x0 at the end. And now we have some strange terms here, but if we look very, very closely and we already know what comes out in the end, we could theoretically see that this is quadratic formula for some arbitrary value a squared, 2ab and b squared. And if we connect the dots and we already know what comes out, we can about get this right here for the acceleration part, and then this for the velocity part, and the x0 for the x part. So if we want to do it step by step, that's okay, but you have to be very exactly, you have to look right exactly right here, and it's quite difficult to get it right. If you either do it without the t0 or you skip this step, it's quite easy actually. In the end, you will always get either this or this formula, and we are going to use those two formulas very much, because they're very important. They are just constant accelerations, and we can always use these two formulas, which is very, very nice. And of course, if we want to do it for vectors, there's nothing that changes, only that we draw vector lines over here. So that's actually what we physicists use every day, this formula right here, just with vectors, and sometimes more difficult. But what can we actually calculate with this formula? It's an interesting formula, but what can we calculate? So I've given you a task, which is a car drives 44.74 miles per hour. It stops in front of a crosswalk, and the second car is now coming with 71.582 meters per hour, and it only reacts after 1 second after the first car has started braking, and it's 92 meters behind the first car. And the question is, does it stop in time? So does it stop before the crosswalk? And I assume just that the cars decelerate with a constant acceleration of 4 meters per second. And if they decelerate, the acceleration is actually minus 4 meters per second. So let's see what we got. We got the x0 and t0 of 0 meters and 0 seconds. I don't say we start to measure 10 meters after our start, or I don't say we start the time 10 seconds after something had happened. I say we start at 0 meters, 0 seconds. So the initial velocity right here is 20 meters per second. That's miles per hour translate it in meters per second, and you see why it shows this strange number here. And now, if it stops, we actually also are given another piece of information, which is that the velocity when it has stopped, or at the time it stops, is 0, because it stopped. That's not moving anymore. So the velocity has to be 0 meters per second. So now a second car comes with 71.582 meters per hour. And you can once again see why it shows that number, because it's 32 meters per second. Now it reacts after 1 second. What does that mean? And that's very interesting. It does not mean that the t0 of the second car is 1 second, because the second car still drives from second 0. It still drives from the 0th second, but it reacts after 1 second. So that's a different. We don't start to measure the second car only after 1 second. The car still drives between 0 seconds and 1 second, only that in this time it has not decelerated. So that's actually a t tilde time, which is the delay for deceleration in total. So the 92 meters behind, however, are initial conditions, because the car, when we start to measure, is 92 meters behind. So that's our initial x condition. Does it stop in time? That's just a question. And our constant deceleration acceleration of 4 meters per second, which is minus 4 meters per second of acceleration. So let's get to calculator. So one interesting thing is, with these types of tasks, acceleration, deceleration tasks, you almost always have to start with the time and then get the values you want afterwards. So for example, right here, we have to start with the time, which is we calculate how long it takes for the car to stop, and then we can get how long it needed to stop, how long the braking distance was. So let's start with the time. The time is pretty simple. It's v divided by a. So you have 20 meters per second, and then you divide that by 4 meters per second squared, and you get 5 seconds. So actually, as I said, the acceleration is minus 4 meters per second squared. But if you look at this formula right here, which uses everything and uses the initial conditions and so on and so on, you can see that my time is actually minus v0 divided by a, or v0 divided by the positive a, by the positive acceleration, which is fine, I guess. So now we know what the time is that the car needs to stop, and now we can get the braking distance. So we just calculate it with the formula of 1/2 a t squared plus v0 times t plus x0. So this is 1/2. The minus 4 meters per second squared is a. The 25 seconds squared is t squared. This is v0, this is t, and there's no x0 for the first car, only for the second. So what we get in the end is 4 times 25, that's 100. 100 divided by 2 is 50, and 20 times 5 is 100. So we get minus 50 meters plus 100 meters, which is equal to 50 meters. So the crosswalk is 50 meters in distance. Now let's jump to the second car, because the second car is a bit more interesting. Now the second car also decelerates at 4 meters per second, but per second squared, sorry. But the actual velocity, the starting velocity, is 32 meters per second. So it takes more time to decelerate, which is 8 seconds. Just 3 more seconds to just decelerate. The question is, are the 92 meters enough for the car to decelerate fast enough? So we get the x of t stop, so we calculate where it stops. We calculate the braking distance by 1/2 a t squared plus v times t plus x0. Now there are some interesting things in the second calculation. The minus 4 meter per second squared is the acceleration, the 1/2 is the 1/2, the 46 seconds squared are t squared. But now we get to v0 times t, but this is not t. This is actually t plus t tilde. Why is it t plus t tilde? Because we chose that the car actually drives for 9 seconds. It decelerates for 8 seconds, so 8 seconds squared is this, the deceleration time, but the actual driving time, which is multiplied with the v0, is actually 8 plus 1 seconds, so we have 9 seconds. And the x0, as I mentioned before, is minus 92 meters. So what we get there is some strange equation, we calculate it, and it's 68 meters. So 68 meters, what does it mean? Well, pretty simple. It means we have overrun whatever pedestrian was on that crosswalk. But how fast have we overrun it? Because I'm not sadistic enough. I have to overrun the person, and then I want to know how fast have I overrun the person that was standing there. Well, let's calculate it, because we can. So now we have another calculation. How do we know how fast the car was when it was there? Well, we have two types of given information. The first type of given information is the deceleration and the initial speed. The second is that we want to get 50 meters far, and we want to know the velocity at 50 meters. So once again, we start with the time. We plug into the formula a random time, we don't know the time yet, and we want to get 50 meters far. So a braking distance of 50 meters and a time, and we want to know how much time it takes to get to these 50 meters. If we were to plug in 60 meters right here, 68 meters right here, we would get that t is equal to the 8 deceleration seconds. Now, if we do this without the 68 meters, but the 50 meters, we get how long it took to get to the 50 meters. Now we take some math. Basically, we multiply it by 1 over minus 2 meters per second squared, the whole equation. Then we get this. Then we have to break apart this, and then we get this back here, which is quite important. This quadratic equation. And as you know, quadratic equations, we can solve that by simply using the PQ formula. And we get t is equal to p halves, that's minus 16 halves, that's 8 seconds, plus minus p halves squared, that's 64 seconds squared, and then minus q, which is 55 seconds. So we get 8 seconds plus minus this strange squared. But don't worry, I chose the values so that this equation actually works. So 64 minus 55 is actually 9. So 9 seconds squared, the square root of that is just 3 seconds. So 8 seconds plus or minus 3 seconds, which is 5 seconds or 11 seconds. Wait a minute. So the car slows down and it goes 50 meters far. And it takes either 5 seconds or 11 seconds to do that. So what happened? It's like in one case, like some deity intervenes and says, oh, you can't already have been at 50 meters, so let's add 6 seconds right here. It's like nonsense. Total and utter nonsense. Why do we have 5 seconds or 11 seconds? Well, the answer is actually a bit difficult. We have not assumed that the velocity can not go under 0 meters per second. So what actually happens is the car drives and drives and drives and slows down and slows down and slows down and gets to the 50 meters right here, then gets to the 68 meters, but then further decelerates and starts to go backwards. And then we get to the 50 meters once again. So that's why we have 2 times right here instead of simply 1. So what do we have to do? Well, we have to choose the right one. We know that after 8 seconds the car is already stopped. So 11 seconds doesn't make much sense because that's after the car is already stopped. So 5 seconds can be the only logical choice. Now let's calculate the velocity. The velocity is just the initial velocity minus a times t, or in the normal case plus a times t, but our acceleration here is negative. So we get the velocity is 32 meters per second minus 4 meters per second squared times 5 seconds, which is 12 meters per second. So what does it say? Well, once again, it doesn't say anything, but we can make it say something. So 12 meters per second is about 26.84 miles per hour, and depending on who you trust with your studies, you actually get that is 4 to 9% mortality rate. So that's actually, if you're one of the 20 unlucky drivers, you actually just killed someone because you were going a bit too fast. But definitely, if you're any driver, you seriously injured someone. So driving too fast is not a good idea. That's what physics says. Now that's quite interesting. Physics allows us to say something about reality. That's what it always does. And it can do that in very simple ways. The velocity is 12 meters per second, or it can do that in very complex ways. And it can say something like, you injured a guy. You just have to calculate and calculate and calculate and get a bit further and a bit further and a bit further and interpret the calculations, and then you actually get a real meaning out of physics. So physics is not just numbers, 12 meters per second, but it actually has a meaning. The first meaning was that we overrun someone, and the second meaning is we actually know how likely it is we killed that someone, or how likely it is that we actually seriously injured someone, and that was like above 99%, so I said definitely. So what do we want to remember? What do we want to remember from this lesson? And I always do these at the end. I always say, what do we want to remember? Because that's quite important. We have been thrown at with lots of details, but we actually only want to remember what's important. So what was the most important part of this lesson? Well, the first important part were actually these formulas. Without these formulas, you're never going to be able to calculate something. So we want to know these formulas at any time. Then we also want to know this formula, because this formula for constant accelerations and our initial conditions, either without t0 or with t0, that's the lower one here, we actually always want to have that for constant accelerations. And mostly in physics we assume constant accelerations. That's like 50% of the time we have a constant acceleration, and we could use this formula right here. And the other times we use the definitions and we get this upper formula right here, which we don't need to remember because we can just use the definitions. So either we use the definitions or we use this formula for constant accelerations. Now these two things are pretty important, so you should definitely remember them. But there's one more thing you should remember from this lesson, which is how you take these tasks with acceleration and deceleration and time and distance and so on. How do you do them? Well, in 90% of all cases, you first have to get the time it takes to do something. The time to reach the highest point when you have thrown a golf ball. The time it takes for your car to stop. The time it takes for your car to reach 50 meters. The time it takes for your golf ball to land on the ground again. You always have to take the time at first, and then afterwards, then you can get the distance or the velocity. Then you can get how far has your golf ball actually traveled? How high has your golf ball actually traveled? How fast was your car when driving over the crosswalk? How far has your car actually traveled? So you always, or in 90% of cases I should say, you take the time first to do something, and then you get what you actually wanted. For example, the distance or the velocity. That's a tip I can give you, because I've experienced lots and lots of tasks and nobody says that. Like, I'm probably the only one that tells you this little secret, but this works in about 90% of the cases, so it's a good place to try to start, and if it doesn't work, you can always try something else. Now, this was everything, and I really hope you enjoyed it. We are going to see each other in the next video. And have a wonderful day. See you all